Okay, let's be real. You open up your physics homework, you see a motion graph, and it just looks like a bunch of random lines and curves, right? It can feel like you're trying to crack some kind of secret code. But what if I told you that you only need one single tool to decode every single one of them?
Well, that's what we're going to do today. In this explainer, we're going to hand you that one powerful tool. And I promise, by the end of this, you'll be able to look at any motion graph and just see the story that it's telling. So let's jump in.
So, what's the big secret? What's the master key that unlocks all of this? It's the slope. Seriously, that's it. Once you understand what the slope of a line is telling you, everything else just clicks into place. It is the single most important idea for analyzing these graphs.
So, quick refresher. What even is a slope? You definitely remember this from math class. It's just the rise over the run. In other words, it's how much the graph changes vertically, on the y-axis, divided by how much it changes horizontally, on the x-axis. That simple ratio, that's everything.
And right here, this is it. This is the one tool. Just think about it for a second. What's the definition of velocity? It's the change in position over the change in time. And what's the slope of this graph? It's the change on the vertical axis, position, divided by the change on the horizontal axis, time. They are literally the exact same thing. So on a position versus time graph, the slope is the velocity. And using that same exact logic, if you have a velocity versus time graph, the slope is the acceleration. This one idea is your key.
All right, enough with the theory. Let's put this new tool to the test. It's one thing to talk about it, but it's another thing to actually use it. We're going to start with a nice, simple, straight line example featuring a very, very fast car.
Check this out. This graph shows the position versus time for a jet-powered car. Now, look at that line. It's perfectly straight. What does that tell us? Well, a straight line means it has a constant slope. And since we know the slope of a position-time graph is velocity, that means the car is moving at a constant velocity.
So, how do we find out what that velocity is? We just calculate the slope. And the process is always the same. First, you pick any 2 points you want on that line. Second, you find the rise, which is just the change in position between those points. Third, you find the run, the change in time. And finally, you divide the rise by the run. That's it.
Okay, your turn to play physicist. Let's use two specific points from the data. The first point is at half a second and 525 meters, and the second is at 6.4 seconds and 2,000 meters. Your mission is to calculate the average velocity. Remember, it's just the change in position divided by the change in time. Go ahead and hit pause right here and work it out. You got it? The answer is 250 meters per second. That is incredibly fast. How did we get that? We just took the final position, 2,000 meters, and subtracted the initial one, 525 meters. Then we divided all of that by the change in time, 6.4 seconds minus 0.50 seconds. Rise over run. See? You totally got this.
Okay, so straight lines are pretty easy. But let's be honest, in the real world, motion isn't always so neat and tidy. What happens when the graph isn't a straight line? What do we do when things get a little curvy? This is where our one tool really starts to show its power.
A curved line on a position time graph simply means the slope is changing from moment to moment. And if the slope is the velocity, then a changing slope has to mean a changing velocity. And what do we call a change in velocity? That's right, acceleration. The curve itself is telling you the object is accelerating. So how in the world do you find the slope of a curve at one specific point? We use a cool little mathematical trick called a tangent line. All it is a straight line that just barely kisses the curve at that one single point. The slope of that tangent line tells us the instantaneous velocity, the velocity at that exact moment in time. Let's actually see this. Take a look at the start of the motion, down near the bottom of the curve. If we draw a tangent line right there, it's pretty flat, right? Kind of shallow. A shallow slope means a low instantaneous velocity. The car is just getting started. Now let's jump ahead to a later point in time. Look at the tangent line now. Whoa, it's much, much steeper. And a steeper slope means a higher instantaneous velocity. You can literally see the car speeding up just by watching how the tangent line changes. It's a perfect visual for acceleration. Now imagine we did this for every single point along that position curve. We'd calculate the slope, get a value for the velocity, and then plot all those velocities on a brand new graph. We'd get a velocity time graph. And if that new graph turns out to be a straight line, what does that tell us? Well, let's go back to our one tool. The slope of a velocity time graph is acceleration.
So a constant slope means constant acceleration. Okay, you've handled straight lines, you've tackled curves, you have the one tool you need. So now it's time to put it all together and analyze a complete story of motion, from start to finish.
This position versus time graph right here tells a whole story about some object's journey. You can see where it moves forward, where it takes a break, and even where it comes back. We can figure out every single part of this trip just by looking at the slope.
So here's your task. I want you to look at this graph and identify 3 things. First, where is the object moving the fastest? Second, where does it completely stop moving? And third, at what point is it moving backward? Remember, think about the slope for each part. Go ahead and pause here to really analyze the graph.
All right, let's break it down. It all comes back to the slope, doesn't it? The greatest velocity happens in that first section, where the line is the steepest and pointing up. The velocity is 0 in that middle part, where the line is totally flat. It has 0 slope. And finally, the velocity is negative in that last segment, where the line slopes downward, showing that the object is moving back toward where it started.
You know, if you only take away one single thing from our time together today, let it be this. The slope of the graph of displacement x versus time t is velocity v. That simple sentence is the absolute foundation for all of this. Burn it into your brain.
So you now have the key to decode motion graphs. My final question to you is this: where else can you use this tool? What other relationships in science, or maybe even in finance or economics, could you understand just by analyzing the slope of a graph? Turns out, this idea is everywhere. The possibilities are pretty much endless.